situation where like some days in your week are busier than others or whatever, but for me that's a Wednesday. And I guess between having 3 hours of class by the time it's noon, I have, well, the 2 hours of office hours, and immediately after I actually have to go to a committee meeting online, of course. So I'll be sitting here a lot, and normally I get to like go places, or at least I get to like stand during class. So yeah, this is gonna be a lot of sitting for today. I went and just took a little walk around the outside world where the weather's nice and crisp here in La Crosse. This thing on the screen. There we go. 6, 5, 4, 3. All right, welcome back. I moved my timer to the other monitor so I can keep track of time. Let's see. So as you'll find that I'm gonna start every day. If we were just meeting in person, I wouldn't do announcements every day, but I think it's a good idea right now because people will be joining in different formats. So sorry to do this, but I guess not a lot of announcements. The one thing I should add to this list first is there will be an online quiz for tomorrow, so it'll be available midnight to midnight. Sometime in that 24-hour period, just do that online quiz. But I just want to say that I want you to hang in there. Keep up that hope. I've been answering a lot of emails from people. I've been answering emails for things that have been mentioned in class, and I say this in quotes, of course. I've already said some of these things by email, and that's okay. Some of the things I haven't, and so I've had to fix a couple things in Canvas or whatever, and just let me know if something comes up. I want to address your concerns, and I don't care if it's something that I've already addressed or whatnot. Like, I think these are challenging times, so I actually kind of expect to be answering a lot of questions. Just ask. It can't hurt to ask. I'll do my best to answer emails as quickly as possible. But yeah, just ask. There's actually, I expected emails, but I wouldn't say that it's taking any more time than I expected, but it is taking up time, but that's just how it is. So please just send me an email if you're unclear about how something works, and let's figure this out. Okay, so the warm-up question today is, look at this function f of x equals 1 over x squared minus 2x minus 3. And that function, where is it increasing? Where is this function decreasing as well? So increasing, decreasing information, we are going to need the first derivative. Since unfortunately our function is a fraction, or a quotient if you want to call it that, we've got to apply the quotient rule. So bottom times derivative of the top, that's why you see that 0 in parentheses. That's the derivative of that constant 1. Minus top times derivative of the bottom. The derivative of the bottom you see in parentheses is 2x minus 2. And this is all over the original denominator squared. Now, if you take a look at this 0 for a moment, well, 0 times whatever is just going to be gone anyway. So that the stuff before the minus sign is going to be gone. And then you could ignore this 1, of course. I just wrote this one in as a reminder that we were using the quotient rule. But if you ignore that 1, you could distribute this minus sign into the positive 2x and to the negative 2. So you'll get a negative 2x and a positive 2. The way I wrote that was I just wrote the positive 2 first. So I have 2 minus a 2x all over. The denominator just stayed the same there. Lastly, as is the usual story and what we've been doing this week, factor. Factoring is going to make our sign chart business a lot nicer. So the numerator, you'll notice both of the terms have a 2, so we'll factor out a 2. For the denominator, let me just, since I do have space here off to the side, I'll write now this x squared minus 2x minus 3. And that factors in sort of this usual format of like 2 sets of parentheses. But then because the thingy that we have is squared in the denominator, we'll just apply that square to both sides. So when you do that, this exponent 2, you normally can't distribute an exponent, but because we got a multiplication there, now you can. And I think it'll be easier to argue when I just reveal on the next slide what happened. So in the denominator, see the thing is, your x squared minus 2x minus 3 would normally just factor as an x plus 1 times an x minus 3. But because you had this square there, then you actually have an x plus 1 times x minus 3 times another x plus 1 times another x minus 3. And if you just juggle the order of those multiplications, you can call it x plus 1 times itself, or squared, and then x minus 3 times itself, or squared. And then in the numerator, as we were just talking about, I factored out a 2. So you have 2 times the quantity 1 minus x. Sorry if that was a little rushed as far as how all that factoring works, but just kind of double check that. When designing a sign chart for f prime, we should ask 2 questions. Don't just automatically include x equals 0. You want to ask always 2 questions. One question is, where's f prime undefined? The other question is, where's f prime 0? So let's deal with where's f prime undefined first. So when would f prime be undefined? Well, f prime over here is written as a fraction. So the question, I guess, becomes what value of x might cause us to accidentally divide by 0? Or what values of x should not be allowed? And it looks like if we plugged in a negative 1 for x, we'll have a problem here, because we'll have x plus 1 would be a 0, and that squared would still be a 0. And then it looks like 3 would be a problem. So we shouldn't plug in 3 for x, and we shouldn't plug in negative 1 for x. Either of those would cause the horrible problem of having a 0 in the denominator. So x equals negative 1, x equals 3. That's where f prime is undefined. And then where is f prime equal to 0? Well, what we should do is we should... so the question we just answered, where's f prime undefined, is morally, it ended up being what x values make the denominator 0. And as we saw from yesterday, f prime set it equal to 0. If you set this fraction equal to 0 there, you get to multiply by the denominator on both sides. We basically end up answering where's the numerator equal to 0. And the only value of x that's going to make the numerator 0 is a 1, due to that 1 minus x factor. So these 3 values of x, which are a negative 1, then a positive 1, then a 3 in numerical order, those are the only numbers to include on a sign chart for f prime. So you'll notice that 0 is not included, x equals 0 is not included. If you were to, it would be a mistake. Please don't do it. I'll just do it for a moment and then erase my work. Please don't include a 0 like I just did. What that causes you to do then is go like, well, I need to pick a number over here, 0.5, and it just gets messy. So the only x values to include are those ones that are answers to these questions. Where is f prime undefined? Where is f prime equal to 0? Okay, and then now we're going to need to pick some x values. And even when picking x values, sometimes people are tempted to write those numbers in here. But if you draw the tick marks, it starts visually, it looks like you're cutting up the number line extra. So try to avoid that, because I've seen people do that and then go, wait, did I pick the right x values? And then, if you're going to do anything, maybe just draw an arrow there or something. You got to pick maybe 0. Seems really natural to pick between negative 1 and 1. 2 would be very natural to pick between 1 and 3. Bigger than 3, probably most people are going to pick a 4. That sounds very natural. Oh yeah, and then we should pick over here also, pick pi a negative 2, just a number to the left of negative 1. So I picked those numbers, negative 2, 0, 2, and 4 for x, and I plugged them into f prime. So I didn't write a whole lot about it because, again, it can be messy to write a little too much. So maybe what I'd like to just take a moment to do first is talk about, let me explain. We've got a plus sign in the denominator in all 4 of these. That's because if you look over here, the denominator is something squared times something squared. So look, if this denominator is just squared stuff, whenever you square something, you get a positive anyway, right? So that should explain the pluses that are in all 4 of those denominators. The numerator, though, 2 times quantity 1 minus x. Yeah, go ahead and plug in negative 2 for x, and then plug in 0 for x, right? And plug in 2 for x, plug in 4 for x. I'll let you do that. I should not over-explain it. So why don't you just stare at that for a moment? Stare at that circled version of f prime. Plug in some values of x. See if you're like, okay, yeah, I've got a positive on top, positive on bottom, and then a positive on top, positive on bottom, negative on top, positive on bottom. See if that's all working for you. If those. Hope you're, ask it. You can unmute at any time to ask if you're unsure. But I hope staring at those, you're like, yep, those are the signs. So we got a plus divided by a plus, which would be a positive. Same thing again. A negative divided by positive would be negative. So I think here's how we fill in the rest of that sign chart. All right, so a plus, a minus, and a minus. Now that we know where f prime is positive and where f prime is negative, we can use this information to answer where is f increasing and where is f decreasing. So the plus signs for f prime, this region over here and this region over there are accounted for using this first interval and that second interval. Sorry, it's probably just messy for me to, I'll just do that, right? So those two intervals where f prime is positive, there's the negative infinity to negative 1 interval, and then there's an interval of x values between negative 1 and 1. And we had to union those together. Same thing for f decreasing. You got to look where f prime is negative. Right? So the sign chart information, basically, we lift right off of that information about where f is increasing or decreasing. You might, I know it came up before, but I just kind of want to address it, that you might say, wait, so all x values bigger than 1 are where f is decreasing with the exception of 3. Why don't we just include 3? Technically, we're not supposed to include 3. In the past, when I've graded quizzes and exams, if people include just like a single number, but their intervals are otherwise right, I have not cared about this. I mention it because WebWork probably will care. That's all. So. Okay, so I think that'll do the warm-up. Just maybe I'll wait to see if anybody has a quick question or not. Okay, the section we're in that we're starting today is called curve sketching. First, I'd like to just give the overall process of what this is about. Curve sketching, by the way, is usually the calculus fancy language of graphing a function. In algebra, you may have been required to graph a function, whether your algebra class was last semester or was 3 years ago. You might have had to graph functions then. And there are certain skills that are used in an algebra class for graphing that we should hold on to. And some of these things we have not even really addressed this semester. Like we only had a two days of algebra review at the beginning of the semester, and I couldn't say everything. This is a good time for me to remind you of some of the algebra that we did, and then also hopefully remind you of algebra you've seen in a previous class, but we have not officially reviewed yet. In addition, we have some new calculus techniques, so from the very beginning of the semester related to limits, and then recently when we looked at the first derivative, and that tells us something about f, right? F prime tells us something about f just like in the warm-up. F double prime tells us something about f, tells us about concavity. All of this information is all helpful, all to be put together, all the information all at once in order to graph a function. So that's what we're about to look at. The information that I have on the next 4 slides, I would suggest you don't take very thorough notes on. It'd be a lot to write down all of it right now. And if we were meeting in class live, I have a handout version of this. I need to actually modify it. I've just spent a little extra time. So I'm going to fix the handout so that it fits our current edition of the book. Not that maybe you don't even have the book at home, but I just need to remove some page numbers and this kind of thing. I will get that posted by the end of the day today. So it might be convenient if you go to Canvas and look at that version. But for now, let me just say just in brief overview what we're going to be looking at. What the process of graphing a function or curve sketching is going to use some algebra data like domains and x and y intercepts. And then use limits like from the beginning of the semester to get vertical asymptotes and horizontal asymptotes. Information from f prime tells you where f is increasing or decreasing, like the warm-up. It also can tell you where there's going to be local mins or maxes, and then the second derivative tells you about concavity information and inflection points. So that's the short version. The slightly longer version is this. So the idea is we've seen a lot of these things. Most of the vast majority of what you're going to see in the next 4 slides, we've seen throughout the semester. It's just now it's time to just put it all together and to do something meaningful with it and see how it's going to apply to a major topic next week. So again, I would not write down all of these details right now. Maybe just write down, okay, step 1, analyze f, and just write domain. Like no more than that, just the word domain, right? Okay, yeah. So find the domain. It also, I'll just point out, not that you should write it right now, but finding the domain is helpful in addition because any x value that's right on the edge, like just almost made it in the domain. It's usually these numbers that are written like right next to the parenthesis in interval notation. That x value is likely a place where you're going to get a vertical asymptote. We actually saw that thing come up at the beginning of the semester when we first looked at asymptotes. We'll review it in an example later today. Find intercepts. So this is not a thing that we've reviewed. It's an algebra concept that I'd like to review right now, though. So to find x-intercepts, so on the x-axis, so all along the x-axis here, the y-coordinate is 0. So like, for instance, if I picked, I don't know, let's say this point is 5, 5. If I pick a point that's a little lower, maybe it's 5, 3. A lower, you might have 5, 1. The point is right on the x-axis here. There'd be the point 5, 0, right? So notice that all these points that are all aligned vertically have the same x-coordinate of 5. The y-coordinate keeps lowering. What I'm trying to get at is all along the x-axis, that's where the y-coordinate is 0. So I know this sounds funny to say to find x-intercepts, why would you set y equal to 0? That sounds sort of backwards, but it's really not. All along the x-axis, the points have no height, and the height coordinate, the y-coordinate is 0 there. So then same thing on the flip side. To find y-intercepts, you should set x equal to 0. Again, it seems all backwards, but on the y-axis, where the y-intercepts are, that's where the x-coordinate is 0. The other thing I should just point out right now is this is not an error. This is actually extremely intentional that x-intercepts is plural while y-intercept is singular. So the reason is you can have multiple x-intercepts, but you cannot have multiple y-intercepts, not in the kinds of things we're graphing right now, because we are talking about graphing functions. So this is sort of my sly reminder to just say, since we're graphing functions from algebra have to pass the vertical line test. And if you pass the vertical line test, you can't have 2 y-intercepts. So I say this right now because, in these kinds of curve sketching questions, your final answer is a picture. You're graphing a function, and your final answer should pass the vertical line test. Sometimes what happens, I've seen it happen where maybe due to a little mistake here or there in some of the things that people computed, they drew a picture, and then once I look at the picture, I'm like, wait a second, that's not even a function because it doesn't pass the vertical line test. So sometimes if you get some data that due to some small computational error, it's like your picture looks confusing, you want to step back and go, wait, double check your work in this part or that part, because sometimes the work you have, if there's a mistake, is in conflict with each other, and just use this as an opportunity to double check. Ooh, there's a lot of language here about asymptotes, but this is stuff that we actually did cover before exam 1. So before we even looked at the derivative ever, we were just dealing with some limits, and we'll review this in an actual example, so I don't want to say too much right now. I just want to say that x equals a A fixed x value called a is a vertical asymptote if, when you look at the limit as x approaches that same number a from the left or the right, when you look at a one-sided limit, you get either a plus infinity or a minus infinity. And we'll see this in a full example in a moment. Horizontal asymptote, I want to remind you that if you have a fixed number called b, then y equals b is a horizontal asymptote if the limit of your function as x approaches infinity is equal to that number b. And we'll see examples of this too. This oblique asymptote thing, we never covered it. We're not going to. What I mean to say is I have it there because the book mentions it in its outline of curve sketching, but just ignore it. I will not quiz you on it. It will not show up in a homework. It will not show up in an exam, anything like that. So don't worry about oblique asymptotes. Okay, so this is some stuff that you get from F, right? So the parts A and B up here those are the algebra ideas. Part C with the asymptotes, I know there was an algebra way to think about asymptotes, but the official way to think about asymptotes is using limits, which is a calculus concept. That's step one. I know that was a lot of detail already in just one step. Step two is now... So step one was dealing with f, not even looking at f prime. Now step two is, what about if you have f prime? So you compute f prime, and then you find you should draw that number line thingy. What's it called? A sign chart. A sign chart for f prime. So I just, more than anything else, what you'll see on this slide is maybe a lot of language, but it's all stuff that we have seen relatively recently. The partition numbers of f prime, this comma, maybe it sounds strange to you, but it's grammatically correct. I'm using this slide as an opportunity to remind you of the language. So a partition number of f prime, what's that? Well, it's an x value where f prime is equal to 0 or where f prime does not exist. So those x values, partition number is just a fancy language for those x values that you put underneath the line on your sign chart. Okay, so anyway, so I just, it's a chance to include the language. Like, this is meant to be like a sort of one-stop shop part of the slides. If you look at, what is it, slide number 355, you can look here. And then information that we've seen, like in the warm-up, f prime positive leads to f increasing, f prime negative leads to f decreasing. And then local min and max info. I know we have not focused a whole lot on that, but that's what early next week we're going to keep practicing this stuff that we have seen, like when f prime changes from a negative to a positive, you get a local min. So all this stuff that you're seeing all throughout this slide, it's language that we've used, or just slightly different versions of, but like these are things that we've seen some of already. This is the stuff you get from f prime. Then, next slide, step 3, we'll look at what you get from f double prime. So when you compute a second derivative, if you look here at part A, the language is very much similar to what was on the previous slide. In fact, I'll step back to the previous slide for a second and say, the same thing about like partition numbers, and then whereas f prime positive or negative tells you about f increasing, decreasing, basically the same language here. You build a sign chart for f double prime, you use the partition numbers of f double prime, but now when f double prime is positive, it doesn't tell you f is increasing, it tells you that's where f is concave up. So there's just, if you compare the two slides back and forth, I'll let you do this on your own, you'll find the language is extremely similar. It just, the key change had to be right here to say that double prime tells you about concavity of f. Same thing for part B. If I step back to the previous slide, you can get information about what's going on so we had interval information over here, but then if you have sign changes in f prime, that tells you something about f. Same deal. If you have sign changes in f double prime, take a look. If your f double prime changes from a minus to a plus, then in your original function f, you go from a concave down to a concave up situation, which I try to write about in the square brackets here. So if you have that change from concave down to concave up, that's where you're going to get an inflection point. In fact, the language I used for an inflection point here is a little different than anywhere else I have so far. An inflection point is a point. And so I wanted to clarify here that you see the x coordinate is called c. Let me erase what I have here so far. But this part, the x-coordinate is c, right? Because the change in sign for f double prime, if this happens at c. But what about the y-coordinate? This is a place where people tend to get confused. An inflection point is a point, and what is the y-coordinate? Sometimes people try plugging in that c into f double prime. You'll notice here, I've got, that's not f double prime. This is the original function f. So what am I trying to say here? An inflection point is a point in the original function's graph. So if you know, so you use f double prime to find that special value of x called c, but once you know what x value you have, and we're calling it c right now generically, you got to plug that c into the original function f to find a point that's on the graph of f. Right, so that was the point I wanted to emphasize there. I know there's a lot of detail to sort of be taking in, and then once you've done that, you've got, so step one was stuff from f, domain, intercepts, asymptotes. Step two was stuff from f prime, increase, decrease, local mins, local maxes. Step three was second derivative, so concavity and inflection points. Now you put it all together. That's the short version of this. I mean, it's a lot to do. Don't get me wrong, right? So I think one of the most helpful pieces of advice I could give is this part one here. Plot the local maxes and the local mins. I mean, get the points. So like, let's say you know you have a local min at a specific x value. Well, then go back to the original function, plug in that x value, see what the y value is. So then you have a specific point that you can graph in the function, right? Because it sort of helps anchor the picture. Same thing with your inflection points, right? So if you already computed the inflection points, so you have points that are in the original graph, go and plot those as well. So it helps to have specific points. Go, I know that my graph goes through this point, at this point, at this point, and then you can draw the rest of your picture based on that. Okay, so we're going to apply this overall process. We've got 31 minutes left, and it's going to take most of the time to just do that for this example. So I've got the function f of x equals fraction x plus 6 over x minus 3. And I'd like to just apply the process from beginning to end. So the first thing that I always do, it's first in that list, but it's like even reactionary, it comes to me, is to look at the domain. I want to ask what values of x work and what values of x don't work. Looks like all values of x work except for 3. So all reals except 3, it's fine to put the domain information in words like this. Of course, you can also put the domain information in interval notation like this. In fact, this interval notation, this is what I was talking about with the number 3 that's next to a parenthesis. This 3 is like just on the edge. It's like if there's a cliff, the 3 is just hanging out right there. It's like it's not in the domain. It's just like holding on. So that's where there's a good chance there's going to be a vertical asymptote. But we'll look at that later. Okay, so we've got domain. The next thing I wanted to look at is intercepts. At least that's what it will be in the handout that I'll create and post. So x-intercepts, set y equal to 0. This thingy here, where you see the f of x, I know we haven't said it this way a whole lot, but you may recall from algebra that where f of x is, you could call that a y instead. So if we just replace the f of x with a y mentally, and then to get x-intercepts, you got to replace y with a 0. Then this place where I just wrote a y, we're going to plug in a 0 instead. So set y equal to 0, you get a thing that looks like this. 0 is equal to x plus 6 over x minus 3. We have here an equation with fractions, so we should, as usual for an equation with fractions, I like to multiply both sides by a denominator that I see. So I see this denominator of x minus 3. I'm going to multiply by x minus 3 not only on the right side, but also on the left side. So I should have probably written this out in like an example yesterday or the day before when we were doing this, but it was such a large example, and we had other details to look at then. But if you just want to see it here once, by multiplying by this, what was in a denominator on both sides, we're going to get this cancellation. Nice cancellation on that side. So the right side will just be an x plus 6. The left side, 0 times whatever, is going to be 0 anyway. So this is really awesome. You end up with 0 is equal to x plus 6. Now I know it looks like all I did was erase a denominator. Please be careful and don't think that in the situation where you have more than one fraction, if you just erase all denominators like this, it doesn't work, right? So you gotta, like, there's gotta be a legitimate reason behind it, and what happened is I multiplied by x minus 3 on both sides. So please be careful there. Now in this equation, subtract 6 on both sides. So you have x is equal to negative, oh yeah, I swapped the two sides of the equation. So instead of writing negative 6 equals x, I just wrote x equals negative 6. All right, so there's our x-intercept. I would accept writing in an algebra class of writing an x-intercept this way, just saying x equals negative 6. I'm fine with that. If you need a point, The x coordinate is -6, while the y coordinate, of course, is 0. We did plug in 0 for y. WebWork might be picky and even inconsistent in some questions, wanting an x-intercept one way versus another. Sometimes it just wants the number, -6. Sometimes it wants the point, -6, 0, surrounded in parentheses. So on paper, I'd take either in an algebra class, and well, true here, but I'm not going to ask you just intercept on its own. You're going to be computing an intercept as part of another process anyway. Now let's talk y-intercept. So y-intercept, this should be singular. There could only be one, again, due to vertical line test. So for x-intercepts, we set y equal to 0. So for y-intercept, let's set x equal to 0. So look up here and just replace every x with a 0. So I replace the two x's to the right of the equal sign with a 0. I replace the x to the left of the equal sign also with a 0. You have a 0 plus 6 over 0 minus 3. In other words, 6 over -3, which simplifies to a -2. So the number here, -2, is a y-intercept, or perhaps the other language that the computer system might need is the point 0, -2 is a y-intercept. Either way, and then finally, let's take a look at the only other thing we should look at before we take a derivative is looking at asymptote information. So this is going to be calculus-y. It's going to be limits. 3, as was mentioned earlier, is right on the edge or the boundary of the domain. So x equals 3 might be a vertical asymptote. Might be, might not be. So you don't want to just conclude and say x equals 3 is a vertical asymptote. We've actually seen examples earlier in the semester where just because that number, that x value makes the denominator 0, doesn't cause you to have a vertical asymptote. So at the end, I will remind you of that example that we saw earlier in the semester. What you need to do if you think you have a vertical asymptote, so x equals 3, let's say right now is a candidate to be a vertical asymptote, then you've got to look at a one-sided limit as x approaches that number. So x approaches this number 3. That 3 was put right there. And we need to look at a one-sided limit. Either look at x approaches 3 from the right or x approaches 3 from the left. I tend to prefer looking from the right because usually that means you get to write fewer minus signs down. That's all. So there wasn't going to be much room on this slide. I just copied this limit problem to the top of the next. And instead of revealing each individual thing piece at a time, we've seen a number of these in the past. Your x approaches 3 from the right. Please make sure, I should address a thing from like exam 1 and 2, or exam 1 mainly, you want to pick numbers that are close to 3, right? Got to get close to the ribbon. So like sometimes people are in the habit of picking x is 5 and x is 4. Like, yeah, those are to the right of 3, but not close. You need something close. So like 3.1, 3.01, 3.001. And if you plug those in, you might think, oh, do I got to use a calculator? But just take a look at the number. It's not actually all that bad, right? 3.1 plus 6 is a 9.1. And then 3.1 minus 3 is a 0.1. Now, I didn't write in all of the other arithmetic here because we've seen this kind of thing in the past, but I'll just maybe speak it to say 9.1 over 0.1 is 9.1 over a tenth. And dividing by a tenth is the same as multiplying by 10. So 9.1 times 10, you just move the decimal place 1 over, so you have 91. Follow that same sort of train of arithmetic, and you'll see the next y value is 901, and the next one is 9001. You can guess what the next y value is, and so on. So you'll notice as we pick x values that are closer to 3, the y value starts to explode. It just gets bigger and bigger. So our based on the y values being positive and growing, we're going to conclude that the limit of this function as x approaches 3 from the right, that this limit is equal to a plus infinity. And here's the thing. It was when a one-sided limit equals infinity, that's the dictionary definition of a vertical asymptote, then x equals that number, the number that x was approaching earlier. That's a vertical asymptote. One other matter we should look at before the derivative is horizontal asymptote. So for horizontal asymptote, I know this was a long time ago, right? This was like the 3rd week of the semester or something like that. You take your function and just slap a limit x approaches infinity in front of it. That's just always the calculus way of finding a horizontal asymptote. I also want to remind you, I know it was a long time ago, but these limits as x approaches infinity of a fraction have their own method. So I just want to remind you, I hope this kind of rings a bell, that you got to factor out the largest power of x. So the largest power of x here is just x to the first. So that's the largest power on top and on bottom. So you factor that out. These x's that we just factored out here and here cancel. So that's the only change that went from one step to the next here. And here's where, again, there's so many sort of things from the past that, but like, eventually this limit problem down here that I just circled will split. And eventually you'll be looking at like limit x approaches infinity of 6 over x. And the point is, we saw some theorem that said when you look at limit of a fraction, limit as x approaches infinity, to be clear, limit x approaches infinity of a fraction where the top is a fixed number like 6 and the denominator is x raised to a positive power such as 1, that this limit should just be 0, right? So, I mean, there's sort of a number of old details that are coming into play right now, but the point is using this, something that looked like that might be familiar if you look back to like the practice exam 1 key or the exam 1 key in Canvas. So the limit problem is going to simplify to be a non-limit problem, give you 1 plus 0 over 1 minus 0. That 1 over 1 will simplify to 1. So since we get a number 1, so this limit problem, the limit of the function ends up being this number 1, summarized right there. That number 1 is a horizontal asymptote. Or rather, I should clarify, y equals 1 is a horizontal asymptote. Both for the vertical asymptote and horizontal asymptote, be sure to write that x equals or the y equals. That's an important detail because if people don't write this x equals, sometimes as out of a little bit of laziness, people don't write that. They just write 3 is an asymptote. What I've seen happen, I've actually seen this happen, is people will then on the y-axis draw in a 3 and then draw in, this is an error, of course, to draw in that as an asymptote. Like, wait a second, that line looks horizontal, not vertical. If instead this is not a good place to be lazy, is my point. There are places I want you to be lazy, and I've picked those things carefully to make sure, laziness is okay if it's not going to like lead to potential mistakes. But just leaving out this x equals is a common place where people are lazy, and that laziness leads to making a mistake. So I would encourage you to write that x equals in, not just say 3, because then you get this automatic reminder that it's on the x-axis where you need to write a 3, and then it'll help. Oh yeah, that's where I should draw that vertical asymptote. So yeah, x equals 3 is an asymptote, y equals 1 is an asymptote. Let's just take all the information we have so far. Sorry, I didn't write in blue at the top that the domain was all reals except 3, but we got an x-intercept of -6. We got a y-intercept of -2. We had an asymptote of x equals 3 and an asymptote y equals 1. So I drew all those things in the picture we have so far. It's not much of a picture yet, but those are some of the details we have. So this is a good place for me to just take a breather and see how are we doing. I know there's a lot of detail, so if I'm going to look to see if anybody unmutes a microphone or types a question. Whirlwind tour of a lot of algebra review and asymptote review stuff from the beginning of the semester. Okay, I don't hear a question or see somebody typing a question. So now what? Well, this x-intercept and y-intercept, x-intercept over here, y-intercept that have been drawn in, those are helpful because those are anchors. We know the graph has to go through those 2 points, and then we could certainly guess that the graph just connects this point to that point like a straight line. Well, punchline, it's not going to be a straight line, but we could at least maybe guess that the function's decreasing the whole time. And that might or might not be true, but like, even if the function were decreasing, let's just make that assumption that the function's decreasing. Do we have like a situation where the graph is going to be concave down? Or like what I just drew, or let me erase that. Do we have decreasing yet concave up would be a picture that looks more like that instead. So these are some of the details. So that's even with the assumption that this function is decreasing. What if you had like decreasing, increasing, decreasing, increasing? I mean, who knows, right? Like all kinds of things could happen. So this is where, yeah, we've got just these 2 points here, but let's now compute f prime to find out is f increasing, decreasing, or where, and then look at f double prime to get concavity information, because that'll just allow us to fill in the picture better than just connecting the dots and hoping for the best. So that's what we're about to do now. We'll look at the first derivative. So we've got f of x, just as a reminder, I put it in blue at the top. F of x was x plus 6 over x minus 3. That's a fraction, so we got to take the derivative using the quotient rule. So first times derivative of the second, that's why there's a 1 in parentheses, minus first times derivative of second, oh my goodness, bottom times derivative of top, minus top times derivative of bottom. So again, the derivative of that bottom, the derivative of that x minus 3, excuse me, was a 1. The denominator, original denominator of x minus 3 is now squared. Let's clean this up a little bit. I put the times 1s there to help remind you we were using the quotient rule, but I think the times 1s actually, it's better to ignore them right now to think of like how we're going to use some algebra to simplify. So if we ignore the times 1s, it's good that they're in the slide for, oh yeah, we use the quotient rule. Think about now distributing this minus sign to the x and to the 6. So then you actually really have an x minus x. And you have a negative 3 minus, because you distribute the minus 6. Yeah, a negative 3 and a negative 6. So you end up with a negative 9 over x minus 3 quantity squared. See, if all we were doing was like the exam right before spring break, you just took a derivative and called it a day, then I wouldn't simplify. But we have to do extra things based on f prime, so it's actually convenient for us to do a little simplifying. So here's that much nicer way of writing f prime. Now that we have it, we should answer the usual questions to build a sign chart for f prime. Where does f prime not exist? Or where is f prime undefined? The only value of x that seems to cause a problem here is x equals 3. What about, oh yeah, I'm sorry, reminder here that this is just to remind you of jog the language, have you practice that. This means that x equals 3 is a partition number of f prime. That's just the language. Partition number, just remember, means what x, it's one of those x values that we put on the f prime sign chart. Right? One of those numbers that are written right below the number line. We might get more partition numbers if we answer the other question, where is f prime equal to 0? So let's set f prime equal to 0. Right, set what we computed for f prime, the simplified one, why not, equal to 0. To solve this equation, got to multiply by denominator on both sides. You get negative 9 equals 0. Now, that equation, don't say that negative 9 is a solution. The question here is what value of x makes negative 9 equal to 0? Now, I get that there's no place to even plug in an x, but no matter where you plug in, I mean, no matter what number you pick for x, negative 9 isn't going to equal 0, so this has no solution. So we didn't get any additional partition numbers. The only partition number for f prime is x equals 3. So that's the only number we should draw on the number line for f prime. So there's a 3 written below, and this d above is a reminder that the reason that 3 is a partition number, the reason we wrote the 3 below is because f prime is undefined or does not exist. We need to do the usual thing of picking an x value that's over here to the right of 3 and an x value to the left of 3. So you could pick 2 and 4. I just picked 0 and 4 just because, why not? So I plugged in 0 for my x value, and then I plugged in 4 for my x value in this circled version of f prime up there. You'll notice that the denominator was 0 minus 3 quantity squared. So look, because you got a square in the denominator, that the denominator is positive. And that's for both of these fractions, right? So both fractions, you got a square in the denominator, so denominator is positive. The numerator is negative 9 in both cases. So I hope does this work for everybody, that we get a less than 0, we get a less than 0, or rather we get a negative and we get a negative again. If we take the information we have, that both cases the value of the derivative was negative, both to the left of x equals 3 and to the right of x equals 3, the value of the derivative was negative, we update our sign chart to have minus signs both to the left of x is 3 and to the right of x is 3. those minus signs for f prime tell us that f is decreasing practically everywhere. So it's the honest technical answer is f is decreasing for all reals with the exception of 3, because f prime isn't negative when x equals 3. F prime is actually undefined, D and E, after all, when x equals 3. Again, this is a place where on paper, if somebody in a quiz just said f is decreasing on all reals, I would normally take it. This is the kind of thing, though, that WebWork is probably a little sticky about. So everywhere but 3. In fact, you know what? 3 is not even in the domain of this function. So everywhere that f is defined, f is decreasing. The idea behind this would be that if you were to draw your function, right? So some axes, as you move your pen to the right, you'd also have to always move your pen downward. That's what decreasing means, right? So sorry, this is a terrible picture that I drew off to the side, but that's the general thing. Yeah. So earlier I had sort of said, oh, we guessed that f is probably decreasing. Yeah, this function that we're going to draw is, you're going to see that decreasing nature everywhere. There's one other thing we should do, though, before drawing a picture, is look at concavity. So let's compute a second derivative. We just on the previous slide had our first derivative in a simplified format, looked like this. And you might say, damn, we've got to take another derivative of another fraction. We got to use the quotient rule again. And you could use a quotient rule. You get the same final answer as I do, but actually, I would like to apply a little algebra first to simplify our lives. So I want to rewrite this so that we don't have a fraction. And then the derivative will be much more pleasant, in my opinion. It's a matter of personal taste, but you might say, well, why didn't we do this on the previous one? So let's go back a slide and take a look at f of x up here in blue, x plus 6 over x minus 3. There's an x both on top and on bottom, so there was just like, it wasn't going to be all that convenient to write that differently. But over here, now, so for some miraculous reason, we already took a derivative, and here's f prime, and now we need f double prime, so we need to take another derivative. And look, the numerator is much nicer. There's no x there. That's I think, the neat thing. So it's a matter of personal preference, but because there's no x in the numerator, I'm going to use algebra to rewrite. So you'll notice there's still just the same number of primes as before, right? This is not f double prime yet. This is still just f prime, rewritten. There's a negative 9, and then x minus 3 raised to the negative second power, right? Because I move something from the denominator to the numerator. I need to make the exponent from a positive 2 to a negative 2. The whole point is this new way that f prime is written, there's no fraction. Yes! Don't need to use the quotient rule. I actually don't even need to use the product rule. You could use the product rule if you want, because we've got a product, but that first piece of the product is just a plain old number, negative 9. So I'd rather just copy the number negative 9 using the constant multiple rule, and then differentiate x minus 3 quantity to the negative second. That's going to require the chain rule, but overall, that just seems like a better differentiation problem than using the quotient rule a second time. That's my opinion anyway. So here it is. I copied the negative 9. Negative 9 there is copied here. And then if you differentiate x minus 3 quantity to the negative second applying the chain rule, then you take the exponent, copy it in front from the power rule. You've got to lower the exponent by 1, which is why instead of a negative 2, now that exponent is a negative 3. And then just because the reminder is super helpful, in the chain rule, you still need to multiply by the derivative of the inside. So the derivative of x minus 3 is 1 minus 0. So I wrote that here, this times 1 in parentheses, as a reminder that that I did account for that other piece of the chain rule. Of course, multiplying by 1 doesn't change the value, but it's visually here in the slides to remind you that all pieces of the chain rule I did account for. Okay, even though this is a way to write the second derivative, this was convenient as far as taking a derivative and avoiding quotient rule and all that stuff. I actually personally find it more convenient now to rewrite this thing again as a fraction to talk about questions related to making a sign chart and stuff. I know this sounds strange, but like I keep pushing the functions format back and forth depending on what's convenient at the time. So take a look. Negative 9 times negative 2, I simplified that to a positive 18. X minus 3 quantity to the negative third. I just pushed that back into the denominator, but I had to change the sign of the exponent from a negative 3 to a positive 3. Times 1. Don't need to write anything about it times 1. So I didn't then write all the details for building the sign chart, because we've done a number of these now, but like the usual two questions, you stare at this thingy, that fraction right there, and ask, where is this undefined and where does it not exist? Sorry, where is it? I just said the same thing twice. Where is this undefined and where is this equal to 0? So undefined when x is 3. And then when is that fraction equal to 0? It just doesn't happen because you set that fraction equal to 0 and you eventually get 18 equals 0, which has no solution. So, okay, so then usual story, pick an x value that's smaller than 3, pick an x value that's bigger than 3. I went ahead and picked 0 and 4 for my x values to plug into my f double prime here. Now, I know earlier we had the denominator was a something squared. Please be careful now. The denominator is not a something squared. It's something cubed. So please be careful. Our argument earlier that the denominator is always positive no longer applies. Take a look here. You plug in a 0 for x, and in the denominator you've got 0 minus 3 quantity cubed, or in other words, a negative 3 cubed will be a negative number. In the other denominator, I plugged in a 4 for x, and so 4 minus 3 simplifies to 1. 1 cubed is positive, so 18 over a positive. Yeah, so just be careful. The story's not exactly the same as for f single prime. For f double prime, we actually have a negative and a positive. Our f single prime, you may recall we had a negative and a negative. So the negative for f double prime tells you concave down. The plus for f double prime after x equals 3 tells you f is concave up, right? So you've got some concave down info places, you've got concave up places. And now let's take all of that information, piece this all together. So, so just this is for f. This is my little number line for f. And I just piecing together the f is decreasing practically everywhere. So that's where the decreasing and decreasing comes from. But we just saw that f double prime is negative sometimes and positive sometimes. So that's why you see a CD and a CU. So what do we do is, here is the picture we had earlier. We had these two anchor points that were those are the x and y intercepts. But now that we know that we've got decreasing concave down, well, that Lego piece, that shape looks like this. This is what decreasing and concave down has to look like. So yeah, earlier we were unsure whether the graph did this or that or whatever, but now we see, because we've used our calculus second derivative info and first derivative info, so we've got decreasing concave down. There's not a lot of room in order to draw how that concavity looks, but that concavity, this concave downness, applies all throughout here, and then of course you keep drawing to get closer to that piece of the vertical asymptote. The other part of the graph that we have is decreasing concave up, and so that as a shape looks like this. Sometimes people get in the habit of drawing that shape here, only because we drew sort of roughly in that same spot just to the left. But notice what's going to happen if you do that is this arrow right there, let me not draw it as an arrow. What would happen is actually you'd have a graph that'd be a more complete picture. Now this is actually wrong. The reason it's wrong is there's this extra x-intercept that's created. See, the thing is, we had solved an equation earlier in the process to show that -6 was the only x-intercept. So this is not a place to try to create an additional x-intercept just because it's going to make the picture work. It doesn't actually make the picture work. Instead, the thing to note is that instead of drawing down there, this same shape should just be drawn right here. That's what's really going on, right? Again, avoiding the asymptotes. So that, I hope, helps put together this. We had decreasing and concave down. Yeah, that's a good question. Thank you, Brian. You're curious about how we are going to graph on a quiz or exam now that our class is online. So for an exam, I have been thinking about this. Don't get me wrong. My plan actually so for this week, because I didn't want to change anything right on the fly, but another question came up from somebody else about, this quiz format. Can we change it? Can I show a picture? So I'm going to, over this weekend, work on a setup where people can give pictures basically for exams as an alternate method, but I've got to work out some details there. So sorry. Yeah, thanks for the question. I appreciate it. Yeah, there's obviously a lot of things that's what's been keeping me up at night. All right. So I did draw in the picture here, and this is, I think, the kind of, over here, the picture that I would want to have drawn if I just had paper. I did ask the computer for an accurate picture, and it gave me this. So if I go back and forth, things are a little off, but like, it's because here, this should actually continue more, but I just didn't have as much room on the slide, right? So same, like the asymptote keeps going and so on. The rest of the slides here, these are actually copied from early in the semester. I just wanted this in a convenient place for you to just mention that a horizontal asymptote, by its dictionary definition, is if this limit or this limit. I want you to focus on this one that I've circled twice, though. If the limit of your function as x approaches infinity equals a number b. So this is also copied from earlier. But how do you find a horizontal asymptote? You basically take your function, slap a limit x approaches infinity in front of it. On rare occasion, the other one, but just really stick to this one. And if that limit problem gives you a number, then y equals that number is a horizontal asymptote. Reminder as well, this is also copied from earlier in the semester, that a vertical asymptote, so x equals a number that I've called here c, is a vertical asymptote if when you look at x approaches that number c, either from the left or the right, the result of that limit problem is a plus or minus infinity. So that's really, this is really copied earlier, but it's 4 situations that are summarized all in one. And same thing happened last section. I didn't have time. I thought I might have time to go through all of these examples, but the point is, these are copied from earlier. I would encourage you to just look through, to be honest. I'd rather just end class a minute and a half early. So thanks for the question, again, about exam related stuff. And I'm going to be changing that up a little bit. But not for tomorrow's quiz. I just want to try to create some consistency and common expectations. So see you tomorrow. And again, just a reminder, please do the online quiz that is scheduled for tomorrow.